Hello, so this week's revision focus is all about climate change. First of all, we're going to have a look at this graph which details temperature fluctuations over the last 450,000 years. What I would like you to look at, because a lot of people get confused about this, is this dashed line along the middle. And that says that temperature is 0 degrees Celsius. Now that doesn't mean that average global temperature is 0 degrees Celsius. It means that 0 is present day temperature. And all of the fluctuations along here is the difference in average global temperature compared to today. So that sounds a little bit confusing, but an example is that at this point, about 340,000 years ago, average temperature was around 5 degrees Celsius warmer than it is today. So, in your booklet, the task that I have set out for you is to describe this graph using the T method. So, T is for trend, E is for evidence, and A is for anomaly. So please pause this video now to go and have a go at filling in those blanks in your booklet, and then I will continue on with the explanation after that. So, what you could have put for your trend box is that overall temperature has fluctuated over the last 450,000 years, but temperature is generally cooler than what it is today. So if you look underneath that hashed line, you can see that the majority of the time temperature is cooler than it is today. For example, there seems to be cycles, so we can see these patterns where temperature rises, falls, rises, falls, rises, falls, and so on. Now they're not exact, but I would say that that is a general pattern. So there are times when temperature rises really quickly, so there are periods when temperature is nearly 6 degrees warmer than today. And then there are also times when it has fallen to almost 9 degrees Celsius cooler than today. And then one anomaly seems to be that temperature changes more frequently over the last 50,000 years particularly. Now, we know why that is. It's not any particular reason other than we have the instruments now to read back through these and gain the evidence here. Whereas obtaining evidence for periods a lot further ago is not as straightforward, it's not as easy. We can be more precise, and we'll see why later on. So, a glaciation is a period which is also known as an ice age. So throughout time, when we've had those periods where global average temperatures was up to 9 degrees cooler than what it is today, these are periods called glaciations or ice ages. And the last glacial maximum, the LGM, was around 18,000 years ago. 27% of the Earth's land surfaces were covered in ice at that time, and you can see that by this map at the bottom. You can see that the UK was covered with an ice sheet. Periods that are not ice ages, where global average temperature is a lot warmer than what they are today, are called interglacial periods. Now, if you think back to that graph at the beginning, which showed global average temperature of the last 450,000 years, we haven't just guessed of what that temperature is. There has been actual evidence to support that. So what we're going to do over the next couple of slides is to look at what evidence there is to back that up, to give us that reasoning that temperature was higher at this point, temperature was lower at this point. So the first thing that probably crops to mind when you think of global average temperature and how people measure it is the thermometer. Now, this type of data is really useful and accurate, but sadly it only goes back a few centuries because the mercury thermometer was only invented in 1714 by Daniel Fahrenheit. So where you can see those lines really closely fluctuating on that graph, that is where we have started being able to take more accurate readings. And there are also other things, which we'll do over the next couple of slides, which are available to us, which allow us to gain more accurate readings, and that is to do with radiocarbon dating, but I will go into that in more details in a couple of slides' time. The next thing is historical evidence. So we can use books, paintings and diary entries as evidence. Painting and artwork, specifically from the 17th century, detail pictures of the River Thames frozen and people ice skating on it. Now, we can't do that today because temperatures don't get cold enough for that River Thames to freeze over. So what we can assume from this historical evidence is that temperatures must have been a lot cooler in those times. However, we must also be careful when using articles like this, because we must appreciate that there could be dramatisation and artistic bias. Tree rings is the next one, and the oldest tree rings date back almost 14,000 years. Tree rings grow one ring for every year that it is alive. So you can see here there are lots of rings on this tree, which mean that that tree has been alive for many years. So an example of this is if a tree had 9 rings, it would be 9 years old. If a tree had 100 rings, it would be 100 years old. The thickness between those rings shows you how much that tree has grown within 1 year. So what you can assume from that, or deduce, is that the wider the distance between each ring, the more that tree has grown. And that then means that that year was warmer and wetter than the previous year, because trees grow a lot when it is warm and wet, warm and moist. And that if the weather in that year was cold and dry, the tree would not grow as much, so the rings would be closer together or thinner. The next one that we can look at is ice cores. So the oldest ice cores ever taken or ever retrieved have been gathered in the Greenland ice sheet, which is GIS for short, and that dates back 130,000 years. And also they've been taken from Antarctica, which is a lot longer time period. They can date back 800,000 years. So the best ice cores are obviously, like I've just said, extracted from Antarctica and Greenland. And the way that we use these ice cores is that locked inside ice is trapped air and CO2. I always like to think of this as a fingerprint of the atmosphere. So the fingerprint of that atmosphere is preserved year after year with more snowfall. So the snow falls, lays on top of the ice sheet, and as more snow falls and falls on top of that, it is crushed and compressed tightly to form this ice that we can see this gentleman holding in that picture there. The oldest ice is found at the bottom of the ice core, and the youngest ice is obviously found at the top, because that is where the snowfall has fallen the soonest or the most recently. So scientists can take that core, chop it into chunks, and they can then work out what the concentration of CO2 at each point through time was. Now we know that CO2 is a greenhouse gas which creates a warming effect. It absorbs heat. So if there is more instances of CO2 or a higher concentration of CO2 in one part of the core, then we could deduce from that temperatures were warmer. If there is less CO2, we tend to assume that the temperature was cooler. A final factor, a final piece of evidence that we are going to look at in this presentation is sediment cores and pollen analysis. So these are really good because they can date back millions of years, the oldest being 200 million years ago. The remains of organism and pollen from plants is found in cores taken from the ocean, river and lake sediments. Scientists then identify the species and can work out what type of climate that species prefers, which in turn tells us what the climate was like at the time. And the ages of sediment is worked out by using radiocarbon dating. Now, for those of you that are scientifically minded and can follow this, I'll go into a little bit more detail about what radiocarbon dating is, but it is very complicated and I still get confused about what it is. So, in living organisms, when they die, there is a certain amount of carbon-14 in them, a special type of carbon. And it decays, because it is radioactive, it decays in predictable ways over time. So researchers and scientists can use this as a kind of clock to understand that at so many years after that organism has died, there will be a predictable amount of carbon-14 in that organism. If you've heard of the phrases half-lives, like when we think about Chernobyl, that tells you how long you've got until the carbon-14 has halved. So in a nutshell, the less carbon-14 in an organism, the older or the longer ago that organism must have died. So the radiocarbon dating works by working out how much carbon-14 is left in that thing, that object, that organism, and then you can work out how long ago that happened. I hope that makes sense. So aside from that, I just wanted to have a look at this picture on the left. Now, it's not the best picture, but generally what you can see is a dark bit of sediment, which this was collected from a lake. So that is a dark bit of sediment and a much lighter bit of sediment. Now, I just want to discuss this in a little bit more detail because we can work out what climatic conditions were like throughout this core. So this part is a deeper part of the core and this part is a shallow part. So we can assume that this part is older than this part. And the colour of this means that this is organic material. So dark brown matter tends to be organic. And that means that this existed in a warm and moist time. So this bit would have been very, very suitable for organism life. This part looks a lot more clay-like, and sometimes this can be blue. And that would mean that this is a colder point in time, so formed underneath the glacier. So even just by looking at these sediment cores, you can see changes in geological history. Now what we need to look at is why that climate changes. So on the slide here, you've got volcanic eruptions, sunspots, and orbital change. So what I would like you to do is think about whether you can remember what the natural causes of climate change result in. Do they result in a warmer or do they result in cooler global temperatures? The first one that we're going to talk about is volcanic eruptions. So volcanic eruptions release giant dust and ash clouds and sulfur dioxide, which sulfur dioxide then turns into aerosols once they get into the atmosphere. So these go into the atmosphere and they act as a blanket. And this prevents incoming solar radiation from getting to the Earth's surface, so it's reflected back out into space. An example of when this has happened is Mount Pinatubo, which erupted in 1991, and that cooled that planet's average global temperature by 0.4 degrees Celsius. So what we can see from volcanic eruptions is that they cool the global climate, which I would like you to pay particular attention to this because a lot of people's natural instinct with volcanic eruptions is that they warm the planet because lava is hot, but it is not the case. You've got to think of that ash cloud blocking out the incoming solar radiation, the heat, if you will. The next one you need to look at is sunspots. So, in a nutshell, sunspots are storms on the sun's surface and they mark intense magnetic activity. These storms create solar flares, which then eject hot gases from the sun. increased sunspot activity has been noted at times of increased temperatures and decreased activity in cooler times. So an example of this is the Little Ice Age. So we can see here the presence of more sunspots results in warmer global average temperatures. The next one that we need to look at is orbital change. So the Earth's temperature can change based on how close the Earth is to the Sun. Changes are noted every 100,000 years, and that means that generally every 100,000 years the orbit around the Sun changes shape. So it goes from a circular orbit, like so, to an elliptical orbit, which means that it is more oval shaped. Now, how this affects global average temperature is pretty simple. The further away the Earth is away from the Sun, so at this point and at this point, the colder the temperature. And these are called Milankovitch cycles. So what I want you to think about is if the Earth is moving around the Sun at an equal distance throughout the full year, it'll be warm all year round. If it is having an elliptical orbit, at some points it will be a lot further away from the Sun, so it will be a lot cooler. So this one can change the global average temperature in both ways depending on which type of orbital shape the Earth takes on. The next thing we need to do, so we've looked at natural causes of climate change, we need to have a little think about human causes of climate change. So on the slide there, you have the 4 actions or 4 points of the process of the greenhouse effect. So I would like you to have a go in your booklet of filling in the gaps there for me, please. I'll pause for a second and then you can pause the video and then I'll carry on. So let's start going through these. Number 1 is solar radiation passes through the atmosphere. So it passes through the atmosphere. Most is absorbed by the Earth's surface, warming it. The surface then re-emits some energy as infrared radiation. So it emits energy like so. And a portion of that escapes back into space. So a small portion of that escapes back into space. But some of it is trapped in the atmosphere by greenhouse gases. Things like carbon dioxide, sulfur dioxide. And because they are trapped, they warm the Earth's lower atmosphere and surface. So the greenhouse effect affects the planet because the Earth's average temperature is 14 degrees Celsius. And if we remove that greenhouse effect, the Earth's average temperature would be minus 18 degrees Celsius. So in effect, the greenhouse effect acts as a blanket keeping the planet toasty and warm. Now what we want to know about is what the enhanced greenhouse effect is. And that is the thing that everybody is really, really bothered about in today's society. So what we can see here is that since 1860, since the height of the Industrial Revolution, global average temperature has increased. Yes, it has fluctuated, but generally it has increased. And it has increased from an average of 13.5 degrees up to around about 14.4 degrees. So that is an increase of 0.9 degrees Celsius. Now what scientists have noticed is at the same time as this, the percentage of CO2 in our atmosphere has exponentially increased. So you can see here from 1860, which the other graph is also starting from, CO2 concentrations have exponentially increased. So scientists have deduced that the amount of CO2 in the atmosphere is directly affecting the global average temperature. So what we want to look at next is how exactly humans have affected climate change. So on the board here, on the slide, are two of the first factors. So what I would like you to do before I start going through these is, in your booklet, have a think. How does burning fossil fuels and how does deforestation affect climate change? Which gas do they emit? So pause now. Okay, so the first one, burning fossil fuels. Fossil fuels such as oil, gas and coal contain carbon dioxide that has been locked away in the ground for thousands of years. When we take these out of the ground and burn them, we then release that stored carbon dioxide into the air. Now, we use fossil fuels for a lot of different things. Things like factory work, driving cars, things like that. So they release carbon dioxide. Deforestation is very similar because forests remove and store carbon dioxide from the atmosphere. So carbon is stored within trees and plants. When we cut them down, this means that carbon dioxide then builds up quicker because there are no trees to absorb it through photosynthesis. But this is also a little bit of a double-edged sword because when we cut down the trees or burn them, that carbon is then released back into the atmosphere. So not only have we hampered the trees from removing that carbon dioxide and turning that into oxygen, we've also increased the amount of carbon dioxide in the atmosphere by burning the trees. Next ones is agriculture and cement. So if you could please pause the video now and then have a go at filling these in your booklet, that would be perfect. Okay, so the first one is agriculture. Planting crops and rearing animals releases greenhouse gases. I've just shortened it to GHGs there. So an example of this is that animals produce methane, and they do that when they pass wind. I'll put that in the politest way possible. And methane is 30 times more powerful than carbon dioxide. So if you are a meat eater, that would then contribute 30 times more than carbon dioxide. On the other hand, planting crops, if we use fertilisers such as nitrous oxide, that is then 10 times worse than methane, which makes it 300 times worse than CO2. Cement is the final one because producing cement is another contributor, and it is equivalent to 2% of the planet's entire carbon dioxide emissions due to the rapid urbanisation that is going on across our entire planet. So what I thought you could have a go at now is explaining how human activities contribute to global warming, and this would be around about a 6-mark question in your exam. So I would like you to have a go at doing this using the PDL structure, point, develop, link, and I have given you your sentence starters for each point. So for the first one, I would like you to talk about how we emit carbon dioxide, and another one is how humans emit methane. So your for example part, you are going to include a fact or figure, and you are going to, in the pink box, link that back to the question. So how exactly does that contribute to global warming? So please pause the video and then I will go through it. So first paragraph, we're going to have a look at carbon dioxide. So one big contributor toward global warming is carbon dioxide. For example, carbon dioxide is released through deforestation as trees store a large amount of CO2. This means that a significant amount of CO2 is released because we cut down a lot of trees, which in turn increases global warming, destroys habitats and reduces the amount of oxygen available for humans to breathe. Another contributor toward global warming is methane. For example, methane is released through raising cattle and crop farming. Here's a good statistic. Methane is 30 times more toxic than CO2. This means that as world population increases, more cattle and crops are needed for food and more quickly. This increases the amount of methane being released. The emission of methane is more dangerous than carbon dioxide. Next up, we need to have a look at the effects of climate change. So I would like you to categorise the effects on the board into social and environmental effects. So please pause the video now and then come back and I will pop those answers on for you. Okay, so increased wildfires are environmental. Increased sunstroke and skin cancer, that would be social because it affects people. Desertification is the expansion of arid, dry areas, environmental. Flooding of homes and businesses affects people, so it is social. More extreme weather events, environmental. Migration of insects to new countries, environmental. Melting ice caps, glaciers and ice sheets, again environmental. Mosquitoes come to the UK, so we get increased cases of malaria. So think about this one as the secondary effect of this part. So we've got the migration of insects, which is the environmental, but how that impacts on the people would be increased cases of malaria. So that is social. Famine is a lack of food supply, social. Mass extinctions of many species, which we are already starting to see today, environmental. UK has drier summers, milder, wetter winters, environmental, and increased numbers of climate refugees, social, of course. So then we're going to segue into how we manage climate change. Now there are two strategies to manage climate change. You can either mitigate against it or you can adapt to it. So let's talk about what these two phrases actually mean. If you mitigate against something, if you employ a mitigation strategy, you are trying to slow down and prevent climate change from happening. So you are actively trying to stop it. You are not producing the carbon dioxide and methane. You've just stopped all production of it. The next one is adaptation. So this is changing the way that you live and work to cope with the effects of climate change. You are learning to live with it. So you do not stop the carbon dioxide and methane from being produced. You just figure out a way to deal with the problem. So on the slide here are 9 factors, and I would like you to categorise them into mitigation and adaptation strategies. So please pause the slideshow, and then I will go over those in a second. So the first one is carbon capture and storage, and this is where carbon dioxide is removed from the atmosphere and is then stored underground. So that one is an adaptation strategy because you're not stopping carbon dioxide production, you are just in effect hiding it somewhere else. Afforestation, again, that is an adaptation strategy. So trees are planted with the aim of reducing carbon dioxide from the atmosphere through photosynthesis. So if you employed this strategy, you are acknowledging that carbon dioxide is continuing to be produced, so therefore you need more trees to be able to take that in and produce oxygen with it. So that is an adaptation because you're not stopping the production, you're just managing the production. And renewable energy, so using virtually carbon neutral methods to produce energy. So that is using things like solar panels, wind turbines, hydroelectric power, and that is a mitigation strategy, a mitigation strategy because you are stopping the use of fossil fuels to produce energy. You are using an infinite source. Next one is managing water supply. So water meters can be used to encourage people to use water sparingly as they are charged for every litre they use. So it's an adaptation strategy. People will just be mindful of the amount of water that they are using. Building flood defences. Seawalls and flood barriers can be installed to prevent flooding as sea levels rise. So this one is an adaptation strategy because you are acknowledging that sea levels are going to rise, so you are just dealing with the problem by building your flood barriers higher or installing them in the first place. Next one is using electric vehicles. So cars can be designed to use electricity rather than fossil fuels for power, which then in turn stops the production of carbon dioxide from those vehicles. So of course this one is a mitigation strategy. If you adopt a new diet, so things like veganism and vegetarianism, you stop eating meat and therefore reduce the number of cows which are bred to feed the population. So that stops the cows from contributing methane to the atmosphere. So that one is a mitigation strategy. There is another side to the coin with that one that I'm not going to touch upon right now, but it involves the argument that actually veganism could also be quite damaging because of the increased amount of avocado consumption and other types of plants which are cutting down the rainforest and then that space is then being used to grow one type of crop. But I'll talk about that in another video. Use of biotechnology. So scientists are increasingly starting to use technology to create new crop varieties which are then resistant to extreme weather events. So there is a type of wheat crop and maize crop that has been developed and used in Kenya which can be grown regardless of famines. So that would be really good because then you can feed the population. But again, this is an adaptation strategy because you're not stopping climate change, you are finding a way to work around it, to survive around that climate change, the increase in temperatures. International agreements. So this one you could kind of argue the toss between both a mitigation and an adaptation strategy. And that is due to the success of each. So the outward aim, the initial aim of an international agreement would be a mitigation strategy. So world leaders come together and they discuss ways of preventing climate change from happening. However, quite a lot of the time it ends up being more of an adaptation strategy because not enough is done. So examples of international agreements are COP26, which happened in Glasgow this year, October to November 2021. We had the Paris Agreement, which was in 2016. And then we also had the Kyoto Protocol, which occurred in 1997. So that is all of those discussed, and that is the end of this revision video for climate change. Thank you for listening.